Hi, everyone, and welcome to this week's Crunch seminar. As every other week, this week too, we have two talks from outside. Our first talk, the speaker would be Romit Maulik. He would be talking to us on learning nonlinear dynamical systems from data using scientific machine learning. A little brief about him. He is an assistant computational scientist at Mathematics and Computer Science Division at Argonne National Laboratory. He is jointly appointed as Research Assistant Professor in the Department of Applied Mathematics at Illinois Institute of Technology, Chicago. Previously, he was the Margaret Butler Postdoctoral Fellow at Argonne National Laboratory and has obtained his PhD in Mechanical and Aerospace Engineering from the Oklahoma State University. His interests are scientific machine learning, stochastic processes, high-performance computing with applications to engineering, geoscience, and plasma physics. And luckily, he is my college junior from my university at Birla Institute of Technology. And with that, I would request him to begin. Thank you.
Yeah, thank you so much for the lovely introduction. And thank you everyone for attending this talk and for this invitation. Very, very honored to be here and very pleased to present my work to you. There's a little bit of an update. So starting next July, I will also be a faculty at Penn State. I'm actually going there to the Department of Information Science as an assistant professor. I'll continue to remain affiliated with Argonne as a 25% faculty appointment or sort of guest faculty appointment. So if people are interested in like helping me transition to academia, so please get in touch. I'll rely on all your valuable insights. Okay, so let me just get started, I guess. So this is the outline of my talk today. So I'll start essentially with an introduction and a motivation for why I do the things I do. Following that, essentially I'll be going through two projects, time permitting, which in a sense reflect the different types of problems or data sets that here in Argonne we frequently deal with. And finally we'll have hopefully some time for Q&A. All right, so in terms of the motivation for a lot of the work that's happening not just at Argonne but at many places and beyond, we live in the digital age where tremendous amounts of data are being generated from various sources. For example, over here, this is a simulation I'm running with some colleagues over here using E3SM, which is the US Department of Energy's flagship climate model. So unlike previous computations using E3SM, because of the growing number of growing computational power recently, we are able to start resolving clouds in climate models. Historically, climate projections have not been able to resolve clouds, and it's actually a big question as to how clouds actually affect the cooling of the earth or the heating of the earth. So that's something that's still poorly understood. So but for the first time in a long time, we are able to start resolving these structures. And the amount of data that we are generating from a simulation like this, you can see over here, is 250 gigabytes of data per forecast day. And we actually are running a forecast for 150 years. So we really are generating a lot of data. On the right, you have a simulation that was presented at the supercomputing sort of plenary talk by some folks at ECMWF. Who still use US Department of Energy resources to run a simulation for the weather, not the climate, on a GPU code, which was resolved at 1.4 kilometers. So think of a grid cell on this particular simulation to be 1.4 kilometers by 1.4 kilometers at the equator. And as you can see, these data sets that are being generated are very close to what are being observed by satellites, which are another valuable source of data. There's a whole slew of satellite launches planned all the way through to 2025, which will be also generating practically real-time data. So I guess the motivation for a lot of the work that is happening definitely in my research program and with people who are interested in similar topics around me is how do we actually use these data sets to extract science, right? And that's where machine learning offers some remarkable opportunities. Okay, So I don't have to, motivate the audience on why machine learning is transformative for engineering, for science. There are several pioneers here, listening to this talk. But for completeness, the approach that we are using for a lot of our, analysis or a lot of our science is to actually leverage the technique of surrogate modeling. So over here in the schematic, you can see that it basically summarizes what surrogate modeling is, from a more engineering perspective, but we can relate that to a more dynamical systems perspective just in a moment. So let's say that you have a bunch of design parameters that go into your system. You can, of course, seek to run a simulation of that system and then get your output. But our idea is that if we can collect data from these simulations, then we can fit a easily evaluatable or cheap to evaluate model that then helps us with any sort of downstream process or consumer of this model, which requires repeated forward evaluation, such as sensitivity analyses, optimization, risk analysis, etc. And so you end up getting large benefits, in terms of computational, savings. A lot of the modern codes that we run are extremely, power hungry, computational hungry. So any saving you get by following this pipeline is essentially a carbon credit in your pocket. So we want to look at surrogate models for seeing what sort of science we can analyze we can extract from these very large data sets. However, for a lot of these data sets, for example, let's say you're observing the luminescence of the ocean from using a satellite, which can be done. You don't really have closed form governing laws available in many of these cases. When you do have governing laws, there are a slew of amazing algorithms out there which help you. For example, the pin method or the operator learning method, where you can you can fit a surrogate or a reduced order model, or whatever you would like to call it, for your dynamics. But in many cases, these are unavailable or poorly available or incomplete. And in such cases, what we want to do is build non-intrusive surrogate models for which you may have some intuition about the behavior of the system. Let's say it's a dynamical system, which is chaotic. You know that it's meant to have deterministic chaos, or that there is an inertial manifold that exists in the system, but that's pretty much it. And so in such cases, how can we build scientific machine learning techniques that are useful? Right, so that is the first part of my talk, and this is joint work with Prasanna Balaprakash, who is a computer scientist at Argonne, Chi and Josh, who are fellow early career scientists at Los Alamos, and of course my summer student Alec Lino, who's a phenomenal summer student, by the way, and who works with Mike Graham at the University of Wisconsin. So let's get started, right? So this slide is a little bit of a background about what approach we want to take in actually learning dynamical systems. So you may be familiar recently with a bunch of papers that have been published in the computer science community, who, in my opinion, have rediscovered the adjoint method. So this technique has come to be called as the neural ordinary differential equation. Very briefly, the idea is that if you have observations of a state that varies with time, you can parameterize the dynamical system for the evolution of this state by assuming that the right-hand side is unknown, let's say, but parameterized by a neural network with parameters theta. The idea is to basically find an approximation for f using a neural network or any sort of architecture. Could even be a Gaussian process, right? The way you actually obtain this formulation, if you were thinking of it from a computer science perspective, is that this is a continuous analog of what happens in a feed-forward neural network, where you have the discretization of the neural network into layers corresponds to the discretization of this equation into pseudotime. And instead of actually remembering the state at each layer, which is what is done in classical backpropagation, this interpretation of the feed-forward operation lets you actually use the adjoint method, which was introduced in 1962 by Pontryagin, to train your dynamics, or to train the layers in your neural network. So how does that work? You essentially randomly initialize theta, you get a feed-forward prediction. In this case, the feed-forward is not through forward propagation, but it's through time integration, right? Using your choice of a time integrator. And then instead of doing back propagation, which is the discrete analog of the continuous adjoint method, you solve another ODE back in time to obtain the hidden state, as the computer scientists call it, but in dynamics it's basically the pseudo time solution. And then by computing this one integral over here, you are able to obtain a gradient of the loss with respect to the parameters theta, but that one that scales linearly with model size, and also is computationally expensive, in terms of scaling. So this is a starting point for a lot of the discussions that we'll be having today. Okay, so we naturally ask ourselves this question: can we use this neural ordinary differential equation approach to learn the dynamics of systems where we don't really, let's say we assume we have some information about the right-hand side, but it's incomplete, right? So, and naturally, one thing that the climate scientists that I work with over here asked me to do as a canonical experiment is to look at a chaotic system, right? A chaotic system with some underlying structure. So if you are using time series forecasting methods such as LSTMs or recurrent neural networks or transformers, it's rather common to see that these methods fail out of the box for systems where you have deterministic chaos, because we want to make long-term predictions that obviously will differ in their trajectory, because that's the hallmark of chaos, but they want to stay bounded to say something that is physical. So for example, for the Kuromoto-Shevosensky equation, which is given by equations 5 and 6, you have, of course, your quadratic nonlinearity, and then this sort of linearity on the right-hand side, which if you select a certain domain and a certain discretization, you can get, you can get a stable fixed point, you decay to it, or you could get something like a chaotic attractor. So you have it'll become clear very soon. You have a trajectory which keeps bouncing around on this sort of manifold in density space. And we want to identify that manifold using our machine learning technique. So, how did we actually address this issue? The idea was that, let's say that since you know that the right-hand side of the equation has some information about, you know that there is a decomposition into a linear and a nonlinear term, can we actually introduce that decomposition into that function f, and make it so that the optimization discovers both of these terms separately in the process of this adjoint based this adjoint based learning. Of course, since we know that the linear term is a matrix vector multiplication, we could impose some special structure into the linear term. Remember, the linear term over here is a combination of two terms with different orders. So we could, if we knew what those terms are, we could cheat and specify it. But let's say we just enforce that it's linear through this, through ensuring that it's symmetric and through ensuring what the boundary conditions are. And then we train this particular approach where the nonlinear term is still kept as a black box, a neural network, but the linear term has this sort of structure in it, right? And when we go ahead and actually look at the training, all these methods, right? The method where you fix the linear term, where I call it fixed over here in the sense that I cheat, I know what the linear term is, or where you purely use a neural OD, which is you don't have a linear term, you just have a right-hand side, which is what everybody is doing. Or for example, you learn the linear term and the nonlinear terms together using the optimization. You'll see that during training and for short-term periods, the losses all look identical, right? So, but as we do some more analysis, as you'll see shortly, that the presence of this linear term helps us extract the desired physical behavior from the system. To give you an example over here, so the top row is the true data, so to speak. So for this particular system, we generated multiple initial conditions by sampling on this steady state attractor and evolving the Kuromoto-Shevchenko equation using the actual equations, using a finite difference method, very, very simple. We of course train the neural OD with just the nonlinear term on the right-hand side, and we train the neural OD with the linear nonlinear decompositions, which are the bottom two rows. In the short term, you could see that all these approaches are in the visual norm, but I'll show you quantitative statistics in a while. They all look identical pretty much, which is something that you would see even if you used some other time series learning method like an STM or a transformer, for example. But in the long term, you see that the regular neural OD, despite having the same loss during training or even lower in some cases, these are ensemble results, by the way, you would see these non-physical high wave number striations if it hadn't blown up by then already. So to quantify these statements a little, let's look at some metrics. So over here, I'm showing you the short-term behavior. So I take an ensemble of tests and compute the finite difference trajectories of these initial conditions, and I also compute the predictions from these data-driven methods. And as you can see, in the short term, there's little to choose between these different methods. You could make an argument that initially when we exactly specify the linear term, that's the fixed linear, the green line over here, we are a little better than the other two approaches, but I wouldn't even want to say that. I mean, I'm just saying that in the short term, they're all performing okay. But if you look at the long term, and the way we look at the long-term behaviors, we actually plot the statistics of the second derivative and the first derivative of the state in the form of this joint density function. As chaos sets in, and then you sort of dissipate onto this chaotic attractor, you start to get, at least in the true evolution of the system, you start to get this sort of pear-shaped behavior in the density, which is replicated by this novel neural OD that we have actually proposed, but is not in the regular neural OD, where the neural network has is asked to subsume both the linear and the nonlinear terms.
Romit, can I ask a question?
Yes, please go ahead.
On the objective. So the objective is to replicate the long-term statistics, not the individual trajectories, because obviously you show that in the colorful pictures that's not possible.
Yes, that's the idea. So initially, the trajectories for a short-term duration are captured sufficiently well, but then in the long run, we don't care about the individual trajectories anymore. We care about statistics only.
So what do we mean by statistics here?
So over here, it will come shortly. We have a KL divergence metric, but the idea is that the densities of the joint density of the second derivative of the state and the first derivative of the state, if you just histogram them, right, the histogram of the prediction coming from the machine learning method should be as close to the finite difference method as possible. So that's the idea. But we don't explicitly enforce this in any loss function.
Right.
That can be discovered. Yes.
So do we then guarantee that if this is true for the joint PDF, that we have the right energy spectrum, for example?
We have an experiment for that where I look at burgers. So maybe you can look at those plots and we can chat again, right? For the energy spectrum.
But there's no theory, right? I mean,
there is no theory. At the moment, we don't have any guarantee.
Okay,
we're working on that now.
So that's a hypothesis that basically by keeping the joint PDFs close, the energy spectrum will be somewhat close. Am I stating the hypothesis right?
That is right, yes.
Okay, thanks.
Excuse me, I have a quick question.
Yes, please go ahead.
So when you plot the joint PDF, is this at one particular point X?
Oh, no, this is for all points X in the grid. So at each point X, you will have a value of the second derivative and the first derivative, right?
Okay, and you put them all together and then you just plot the histogram.
Yes, and also for different times. So it's
and for different times too.
Okay. Yes. After you hit the attractor. Basically.
After you hit the attractor. Okay.
After say 100 time units. Yes.
So this is a joint somehow PDF, but it blends information from all the points in space.
That's correct. Yes.
Okay.
Mhm.
All right. Thank you.
Sure. Yeah, feel free to interrupt me at any moment. Okay, so what have we done so far? I mean, so we've done this linear nonlinear decomposition of the right hand side as was shown here, but this actually opens us up to some powerful results, a powerful theory from the early 90s related to approximate inertial manifolds, which lets us actually build a reduced order model of a surrogate. Frequently, these two terms are conflated, so people consider a reduced order model to be a surrogate model. So over here, my understanding is that a surrogate model it preserves the order of the original system, but then by leveraging some structure in this system that you've learned, you can actually reduce the number of degrees of freedom that you have to simulate. So over here, if you know that this is a quick crash course on approximate inertial manifold theory. Oops, sorry. Where if you know that there is a certain set of basis functions onto which you can project your system, which are given by projection matrix P over here, you can actually obtain you can in some sense think of this as a Galerkin sort of approximation or Galerkin discretization, where P corresponds over here to the resolved frequencies which are evolved in equation 7, and Q corresponds to the unresolved frequencies which have to be modeled. You don't want to simulate 8, you only want to simulate 7, but approximate Q in 7 by assuming, for example, in the earliest works, they assume that dq by dt, so the finer scales are stationary. So dq by dt would be equal to 0. And so you can get a first order approximation of Q using equation 9 and setting dq by dt equal to 0 in equation 8. That lets you actually have an evolution equation for your dynamics, which are controlled by the dimension of the projection matrix P over here. So approximate inertial manifold theory says that you can actually construct P using selected eigenvectors of this linear term that you have. So historically, in the earliest results, you would know the linear term because you would know the equations correct. You could perform your eigen decomposition and extract the right eigenvectors to obtain what the projection matrix is. But over here, since we again don't have any sort of knowledge about what the true linear matrix is, we learn it through our optimization. We can actually obtain this projection matrix after optimization to then take our neural OD and obtain what is the equation 7 representation of the neural OD, which is a you can say a reduced order model of the neural OD, which we call an AIM ROM of the neural OD. So, and if you actually were to look at the statistics of how, again, the steady state, the chaotic sort of attractor densities look like, as we increase the number of the number of eigenvectors that we are retaining in the linear term over here, you'll see that, of course, the orange boxes over here correspond to what we are calling purely Galerkin approximation, which means that you just set Q equal to 0 over here. You don't really model the effect of Q on P. And of course, the errors are higher. So the KL divergence over here is a distance metric between the density that was obtained from finite difference method, which we assume to be true, and the machine learning method, which is coming after the optimization and the reduced order modeling. And the errors steadily decay as we resolve more and more eigenvectors. That's expected. The orange boxes are, as I said, when Q is 0. The blue circles over here correspond to what happens if we are actually performing this added operation, this Q equals A inverse capital Q of P, which is the approximate inertial manifold modeling, or the closure modeling, so to speak, in this context, which obviously reduces the error compared to the Galerkin. But then you see there is an inherent dimensionality, attractor dimensionality that exists in this particular system, which is about 18. And so after 18, you see that both the orange boxes and the blue circles are converging because in essence, extract or preserving more eigenvectors is not really helping in the sense of improving the statistical accuracy from these ML models. Okay, so what I have in the green crosses is what is called a post-processing approach. So the idea over here is you simulate your Galerkin approach, which is you don't model Q, but then you know that in order to retain Q from P, you use equation 9. And so after you retain Q, you just add it to P and obtain something in between. So it sort of balances the slightly higher computational expense of the AIM approach, which requires this extra computation, and the Galerkin, which is obviously faster because you don't really care about Q at all. So in some sense, one thing you can sort of gauge from this plot is the ability to actually ascertain that there is this sort of inherent dimensionality of this attractor that you're able to tease out using this analysis. So that was quite nice. But the end result is that if you retain, let's say, 16 degrees of freedom in the sense of the projection matrix, then your original model, which was 64 dimensional, because you had 64 grid points in space, can be reduced to only 16, so a quarter of its size. So we have flipped the script, so to speak. We build a surrogate model first and then reduce this order. Okay, so let's go to another set of experiments. So the second set of experiments is again for a dissipative system, here given by the Viscous-Burgers equation, which is of course a canonical system for performing a lot of numerical studies. Over here, the system is given by a quadratic nonlinearity and a more conventional linearity with a viscosity term. The viscosity that we have chosen for our experiments is 8 into 10 raised to negative 4, so sufficiently low to demonstrate some sort of discontinuities. And what we want to do is do exactly what we did in the previous set of experiments, which is learn this system using a neural OD, and see in this particular case how that helps us with, for example, preventing Gibbs oscillations near the discontinuities and the capture of the scaling laws that exist at such a high viscosity for burgers. So the original set of equations was training data was generated by superposing frequencies in Fourier space for the initial conditions, so sine and cosines, and then discretized on 512 grid points to obtain our so-called truth. So let's apply this this approach I've introduced to you and for a test initial condition and see how the results look like. So again, I have no knowledge of the equations. I just have a linear nonlinear decomposition for the methods that we have proposed, and the regular neural OD learns the right-hand side directly. So one thing becomes apparent: the presence of the linear term definitely acts as a stabilizing factor. So the orange curves that you see over here are caused, you can see these kinks in them, and sometimes the shock location is inaccurate, and that is because of course of the type of behavior that we saw in the previous set of experiments, this high wave number sort of information that creeps in the long-term evolution of this problem. So, but in contrast, the presence of the linear term is actually it's dissipative, as we might expect, right? So this is good news. If we were to look at more quantitative metrics, so over here we are looking at the relative error in the L2 norm sense between predictions and truth for these different approaches. The neural OD, the standard neural OD, so to speak, essentially blows up, as you'll see. Whereas the linear terms stay bounded. Eventually, dissipation kicks in, and then so it's able to actually stay bounded, or as the hypothesis. More interestingly, what we are interested in is the fact that can these these machine learning approaches actually extract the appropriate scaling law, or actually preserve it, which for this particular case for burgers in the presence of these these discontinuities, is a k to the -2 type scaling law, right? As you can see with the regular neural OD, initially everything is air quotes laminar, right? So there is no scale, separation, and there is no scaling law that has emerged. But over time, you get this k to the -2 type behavior. The regular neural OD, basically this high wave number behavior kind of starts creeping into the system, and over time, this basically you end up having it essentially blows up if you run it for too long. But in comparison, the approach that we have proposed over here is actually, you're able to keep that pile up error at the grid cutoff bound rate, which is a nice feature. Yes, George, do you have a question?
Yeah, so I was wondering if you could explain, because we're looking at similar systems for climate, so
Okay.
the QG system and so on, so you have to be careful. But I was wondering if you can explain why let's say at time t equals 1, the long wave number region is worse than at time t equals 5. Somehow the statistics become better later on, or if I run at t equals 10, I will get an overshoot.
So you're saying that, oh, you mean for these very high wave number regions?
No, not the plateau, just before.
So here, the inertial range?
No, just from, let's say, I cannot see the number, but around from 10 to the 1,
okay,
10 to the 2.
Oh, okay. I see.
So that part of the spectrum,
I see.
It looks better at longer times, and I was wondering if you go even longer, would you get an overshoot, or basically you just got lucky for that period?
Yeah, I mean, to be honest, I had not noticed that. We were kind of focusing mainly on stabilizing this pile up, but that's a good point. We'd have to look into that. We did not really dig very deep into this particular region. At the moment, I wouldn't want to offer an explanation to incriminate myself. But thanks for bringing that up.
Sure.
It's interesting. Yeah. Okay. Yeah. So very good point. So the question is, why in this region from near the 10 to the 2 region does the stabilized machine learning method at times perform well, whereas at times not. So yeah, we'd have to look into that. Okay.
There is a kind of explanation for that, because the Berger's equation is a contraction. So eventually the viscosity takes over.
Right.
So if you capture the inertial range well at the beginning, it means that you capture well the cascade of energy. So afterwards, from time 3, 4, 5, when the viscosity takes over, if you know how to feed it with energy, it knows how to dissipate it. So I'm not saying that this is a proof that for later.
I think you're right, because I was thinking exactly the same thing, because if you fix the dissipation, this is a dissipation range, by the way.
Mm-hmm.
Yes.
So beyond the k minus 2, there's the dissipation range. So if you actually fix the linear part, which is the dissipation, and here only you have a second derivative, unlike Kuramoto-Zhivajinsky, that's probably the explanation. And you know that, that's what I was expecting Romit to say, but it's a suspicion, but I think it's true suspicion, because they keep the linear term.
Yes, because you do this particular decomposition that learns the linear term. So you learn the viscosity well, and eventually for viscous Bergers, eventually meaning after sufficient time, it's the viscous term that takes over. So
exactly.
If you do a good job of feeding it with the right amount of energy, it knows what to do with it.
Yeah. A way to check that, Romit, is to look at the shock. Look at the shock that is formed. It's probably formed around time t equals 1 to 2, and then you will see that the shock strength diminishes, which means that what Panos was saying, that viscosity has taken over and dissipation starts. And then that's why you start correcting this range. So it may not be accidental. I think that Panos' explanation is correct. That was my suspicion, but I didn't want to offer it either.
Okay. All right, great.
Let's eliminate Panos.
Okay.
Hey, Romit, I had a question. I'm Raj
sure.
from Rom. So I didn't understand what CNN is doing here.
So this is just a holdover from what we decided to call it. The CNN is actually the method that we have proposed. It's just that the linear term is implemented as a CNN filter. Think of it that way. So that's and the fixed linear is when we cheat and we exactly provide the right linear term, which is in this case, the second derivative. I hope that.
Okay. Thanks.
All right. So so let's move on then. Okay. Another experiment that we ran, because this was explicitly sort of one of the questions that we had when we started this research, is to make these these time series forecasting methods more robust to perturbations, to the initial conditions. So the series of plots that I show you over here with the epsilon over here corresponds to 3 magnitudes of noise that are added to the initial conditions. So over here we sample noise from a uniform distribution, and then basically just add this noise to the initial condition. As you can see, again, the regular neural ODs, basically essentially immediately blow up with the addition of the noise. But as the audience said, since we have a sort of a more dissipative system where we've learned the dissipation properly, we are actually able to stay more bounded in the long run during the test. So that's also a nice property of these stabilized neural ODs. So this could correspond to systems where, let's say that you've learned a system from, say, observations where you don't know the exact equations, and then when you want to do a forecast, the initial conditions are again coming to you from maybe a different type of instrumentation where there's a different type of bias, a different type of noise, in which case you don't want your learning to so hyper specialize on your training data. You want it to be a little more robust. So that's also kind of observed if you use this other sort of linear nonlinear decomposition. And in this case as well, you can see if you're adding noise, then we get similar types of plots where we are able to still stay bounded to the right scaling law and not essentially have this crazy sort of pile up and blow up, which happens with the regular neural OD, because in some sense that is not able to sort of dissipate the noise properly that is added to the initial condition. So we retain this nice behavior. Okay, so in my abstract I talked about how we are actually using these approaches for some more real world data sets, not simply Burgers and KS. So over here we decided to take this method, since it was giving us some nice results, and actually look at a data set that was extracted from satellite and ship observations. This is a publicly available data set on the NOAA repository, which is for the sea surface temperature, the temperature on the surface of the oceans, available from 1971 all the way through to the present day. We subsampled this a little just for computational ease. It's the original data set is 1440 by 720, but we reduced this to 360 by 180. But still a significant increase on the compared to the KS and Burgers, which were order of 100. So what we want to do is do exactly the same experiment again, have this linear nonlinear decomposition, and see if we can actually stably predict this type of behavior for the sea surface temperature. Again, this is a very difficult problem because the sea surface temperature we know is affected by many different parameters. It's affected by wind speeds. It's affected by the maximum temperature of the air, the incoming solar radiation. But we only have access to the sea surface temperature. So in some sense, this is we're setting ourselves up to have a tough time. But there's quite a few people have actually looked at this data set and used it for sort of benchmarking or numerical algorithms, including machine learning algorithms. Okay, so Now, everything I show you after this slide is actually very, very preliminary in the sense that we are still not where we want to be in terms of accuracy or in terms of actually making this something of a sort of a viable tool for climate scientists. But in terms of the trends of the behavior that we saw in the KS as well as the Burger's equations, we are seeing similar types of behavior. So over here, I'm showing you. One thing that I also want to add is for this particular system, we did not take the original grid in latitude and longitude space and show it to the NeuroLOD, though that is possible. It just becomes much more expensive to train our NeuroLOD, but we actually retained 50 POD coefficients, which captured 99% of the variance of the system. But you could use any sort of embedding that you choose to. That reduces the dimensionality of the system while preserving information sufficiently. It could be an autoencoder, could be kernel PCA, and essentially perform the NeuroLOD training on that subspace. So we do a coordinate transformation in layman's terms. And so over here, as you can see with the regular NeuroLOD, this is for a little more information. The training data set is from 1981 to 1990. And the test data set is 1990 to basically the present date. So, and the axes over here on the numbers on the x-axis correspond to weeks. So we are basically plotting it for several weeks. The results that come in from just a regular NeuroLOD show this sort of behavior where you're kind of ended up learning some sort of fixed point type of behavior when we know that the climate does not decay to a fixed point, right? The seasons keep coming, whereas the NeuroLOD with the linear nonlinear decomposition is actually it's not quite as accurate as we want it to be, because probably we have to add more variables to our data set, but it's able to pick up this sort of this invariant, I don't know, climatology type manifold that exists, with the Earth's, sea surface temperatures. You do have this oscillation that happens. Specifically, if you were to say go into the East Pacific and pick up a probe that's far away from any land, and compare, the behavior of a temperature probe in comparison to the operational forecast models that are out there right now. So, for example, the green curve is HICOM, which is a model that is run by the Department of Defense for 48-hour simulations on a very, very fine grid. And then CSM, which is run by a consortium of agencies, but it's a climate model. And you see that when you're running a climate type run, which is you literally initialize your NeuroLOD at 1990, or the NeuroLOD that we pitch at 1991 and have it run all the way through, for 30 years, you see that the regular NeuroLOD, it catches, this frequency. It doesn't catch this frequency properly. It decays. But what we get from this sort of stabilized NeuroLOD is something that is still not accurate. I'm the first one to admit that, but we are in the process of getting there. We are trying to improve this so that we are able to fix these phase errors at the moment. But if you compare to the current climate model that's actually used for the IPCC reports that go to the policymakers for recommendations, then the amplitudes seem to match sufficiently well. And in particular, if you actually look at more sub-seasonal forecast tasks, so the grand challenge of atmosphere or of geophysical modeling is not numerical weather prediction, which is order of days. It is not climate projections, which is order of centuries. It's subseasonal forecasting, which is order of like decades or less, months to decades. In that sort of zone where we reinitialize the initial condition from some observation, then the NeuroLOD actually outperforms like a climate model. So the climate model, this is well known, the climate models don't really do so well. This is root mean squared error in temperature, by the way. The climate models don't actually do well for subseasonal forecasting. They do well for sort of aggregate metrics for over centuries. So this is a promising result, but this, of course, is not quite there yet. So we're still digging into this more and more before we decide to sort of announce this to people. Okay, so I have another section of this talk, which I suppose I inaccurately computed how much fun I would be having in telling you about this first part. So if the audience is so inclined, I'd be happy to go into this very briefly into the second part of the talk, or I'm even happier to stop here and
Romit, you can go on.
Okay, great. All right. So the second part of this talk is work that looks at learning dynamical systems from data sets which are inherently stochastic. So think about a stochastic dynamical system. Can we actually learn a surrogate for the stochastic dynamical system? And we know that machine learning methods, which so far I have shown you are deterministic in nature, would suffer from learning these systems because these systems inherently are not deterministic. So the results I'll show you, or the ideas that I'll be discussing over here correspond to generative machine learning, generative scientific machine learning, where the goal is to learn densities. So the density goes into the objective function specifically, rather than the previous examples where the density matching was just a happy coincidence. So this is joint work with, of course, my colleagues at IIT Chicago, Yanis Kevakidis at Johns Hopkins, and of course, and Felix Dietrich at TU Munich. So a brief background on the types of systems that interest us for learning. So over here we have, for example, a canonical description of an Ito stochastic differential equation. The idea is that you have a state given by X, which is controlled by a right-hand side, which has a drift sort of term, which means that the average behavior of the state changes with time, and then you have a diffusion, which is where B over here is a Brownian process. So at each time step, you may have a like a random sort of perturbation to the state that is added in addition to this drifting that happens. So for systems like this is a stochastic dynamical system. Excuse me. You can write down in certain cases a PDE of the system, which Yanis actually calls a closure, very different from the closure that for example, turbulence modelers use, where you can extract a PDE for the PDF, so partial differential equation for the density, which is governed by, excuse me, which is governed by this stochastic dynamic system. So if you were to perform Monte Carlo simulations of dx by dt given an initial condition and histogram these particular state trajectories, you would see that for certain situations where closed form solutions are available, that the computation of equation 14 would give you densities that match these histograms. So that's what's meant by closure. So for cases where you have a Brownian process on the right hand side, you can actually, and of course some assumptions on the nature of for example sigma and the drift. Then for example, drift is only a function of the state at the current time step. It's a Markovian type of term. You can write down this PDE, and this PDE can be discretized using, for example, finite differences, provided X is not very high dimensional, to get your closure or to get a density function evolution without having to do Monte Carlo. But in certain cases, you may have a right-hand side which actually has a non-local or a non-Gaussian component or a non-Brownian component, which we call an anomalous diffusion type of behavior. So you'll have a system, for example, here where you have a drift term, you have a diffusion term, and you have an anomalous diffusion term where instead of a sort of Gaussian type of perturbation, you have a Levy flight type of perturbation. So in such cases, you actually complicate things in terms of writing down the PDE of the PDF, where you have this non-local sort of, it's an integral differential equation. You have a non-local term that comes in as a result of this non-Gaussian perturbation. And in many cases, if I were to relax assumptions even more, for example, make drift a sort of a non-Markovian term, or make these diffusions non-Markovian, then you lose the ability to even write down an equation such as this. So you end up having to use essentially like binning techniques to see how the PDF evolves and start from there.
Romit, there are exact fractional equations that we have derived and other people have derived for it.
Oh, okay, great. So is it also for situations where your drift and diffusion terms are
yeah, with some assumptions, yeah.
Oh, okay, great, yeah. great, excellent. Yeah, so see, it's an active area of research, and it's a question that people are interested in. So our idea over here is, okay, in many cases, let's say that the assumptions are not permitting you to actually write down an equation like this, or the computational expense of actually solving this system in very high dimensions is proving too much of a bottleneck. What can we do with machine learning to actually learn these systems, learn the density of these systems that come from the evolution of these stochastic dynamical equations? So let me skip this slide. I'm sure you're all familiar with the difference between these two. So over here, what we want to do essentially is use scientific machine learning for a Fokker-Planck surrogate, essentially, which is looking at samples from these stochastic dynamical systems, but through looking at these samples, learning their densities. So, for example, there is some work out there already. For example, Dr. Karnidakis has been pushing the boundaries on this. Another one sort of school of thought comes from David Duvenord and Lars Rutorto at Toronto and Emory, where the idea is to use a neural SDE, neural stochastic differential equation, where the terms in this equation are parameterized as neural networks, and you actually learn the evolution of this system by looking at the samples. The problem with that is you still have to do Monte Carlo at the end of the day if you were to actually find the PDF, so you don't actually exactly get the PDF. Dr. Karnidakis has worked on using generative adversarial networks for learning the sampler of these densities. So that is also a very cool way to actually scale to high dimensions, because GANs work nicely in high dimensional systems. And of course, Dr. Karnidakis, you've worked with fractional pins, right? So if you have a system like this, which has like a fractional term on the right hand side, and the structure of these terms, then you can definitely frame it into a fractional pin type of setup and actually learn the density by penalizing the form of these laws. So our approach is slightly different. We want to extract an explicit density in comparison to GANs. GANs will give you the sampler of these densities, and what we want to do is to use a normalizing flow to actually learn these densities. Normalizing flows are previously, before neural networks became such a big thing, they were also called it was also called Gaussianization in some papers, or there are optimal transport papers from the early 2000s which also refer to the same idea. The idea is that you want to learn an invertible transformation between a sample from a well-known density, such as a Gaussian, a unimodal Gaussian, to your target density, which is unknown, right? And this transformation happens from like one region in the domain of your source density to one region in the domain of your target density. So you can actually obtain an explicit relationship for the density. Specifically, if my target density is X and my source density is Z, this invertible transformation makes it so that you can go back and forth between the source and target. And through the law of conservation of probability, you can actually write down an expression for the target density as a function of the source, by conserving this. It's sort of volume conserving type of transformation. What we need over here is to specify as the machine learning modeler what T is, the transformation specifically, so that the probability density of what you obtain from this specified transformation matches what you observe from your training data very closely, right? And when I say matches, I mean matches in the sense of a metric in this, in the space of probability, such as the KL divergence or the Warsh's time distance, something like that. So over here, what we need to specify is T, and the major computational bottleneck over here is the computation of the Jacobian of T, according to this equation, specifically the determinant of the Jacobian. So there is a big sort of body of work or many research groups in machine learning who actually spend a lot of time on finding new ways to find what T is, so that the cost of computing this right-hand side becomes lower and lower. But that's not my prime focus. My prime focus is to learn a stochastic dynamical system. So let's say you've specified this T appropriately. You can then take a log on both sides and compute the difference between the two sides to actually, or you want to maximize the log probability of this or of the left-hand side. So you can construct a loss function such as this. Sample xi from your training data set, push it through this push forward measure, this T that you have specified initially. It's probably got some trainable parameters in it. Go to the Gaussian, where you can easily compute the log probability of this term. And over here, all you need to do is compute the determinant of the Jacobian for, again, that sample value xi. So in some sense, this right-hand side term is the major computational bottleneck. You can also compose transformations if they're all invertible, such as shown in equation 22. And by composing such transformations, you can actually learn some pretty complex densities, because by composing transformations which each have trainable parameters, you get more and more expressiveness in the sense of the map from the source to the target. And so what we want to do in this particular research is to actually have a transformation that A is invertible, B has a very easy to compute Jacobian, and C is parameterized by time, because in our case, the densities evolve with time. So there is a PDE of the PDF that we do not know. So we wish to capture the behavior of the PDF in time. So in comparison with a lot of work that is actually out there in the image generation community, we actually have to make our normalizing flow conditioned on time. And so one way to do so is to use something called it's essentially like a triangular map. It's also called a real NVP, non-volume preserving flow, which was published in 2017. The idea is that from the source distribution for a certain number of dimensions, this could be high dimensional, of course, we have an identity map, but for the rest, you have this sort of invertible mapping, and you can sort of work it out by hand that if you want to go from X to Z, you just need to subtract the mu and divide by the raised to the mu. So that's the nature of the transformation from the target to the source, and then vice versa. Over here, what ends up happening is that mu and nu become our neural networks, right? So they become neural networks that have to be calibrated given our training data. The nice thing about this particular type of mapping is that you get a very easy to evaluate determinant of the Jacobian, which I told you I think was point B. It is a big computational bottleneck, but again, the reason this method was so popular is because the determinant of the Jacobian was very easy to calculate. And so for, if you're thinking of doing this for very, very large data sets, this actually ends up being very convenient. In our case, we also added dependence on time because, like I said, we want to, the density varies with time and we want to capture that. Okay, so let's look at an example quickly. I'm already 1 minute over, so I'll speed up a little. So this is an example where we have a, like a two-dimensional system. We're starting small with a certain drift in the, for each, each component of the state and a certain, levy type process that causes the perturbations at each time step. Some details about how the training data is generated, but essentially what you end up having is a system on the top, which is the true system, where if you sample from the density, you end up getting, an initially unimodal type of density, performs this very cool sort of behavior with sort of 4 modes. All the particles start clustering to the edges of this square. And on the bottom, this is the same behavior that is being replicated by the temporal normalizing flow, this sort of generative machine learning method for learning the same type of density, but now that it varies with time. Of course, we took samples in time at certain snapshots, and the snapshots I'm showing you here are for so-called test snapshots, which means at those times we do not actually have samples. And this has actually been published in Chaos. This is an outdated slide. Sorry about that. So, okay. So another example over here is the canonical half moons data set. So the half moons data set is something you can just import in scikit-learn, and it takes a parameter epsilon, which is no longer time. It's more like the variance of the noise that is added to the half moon data set. So you could assume that time is increasing and this data set is getting more and more fuzzy. And so over here again, you can see that the generative machine learning model is able to sort of qualitatively reproduce the behavior of this sort of this data set, get more and more fuzzier over time, right? We are not, I mean, so far what we have done is not really very, very novel, but what we are looking at the moment that is really exciting is that by virtue of actually having access to T, right, we can start looking at how the transformation actually behaves in the space of the support, right? So if Z is our source density and X is our target, how is a particle that starts at a certain point in Z actually acted on by this transformation in this case, T stands for pseudo time, right? So if the flow map is extractable over here by automatic differentiation, there is a potential connection. Again, this is work underway, potential connection to actually then trying to see what gradients are important, right? So you can actually take gradients of the transformation with respect to time, with respect to space, right? And start trying to extract a dynamical system rather than just merely learn it as a black box. So that's something that we are looking at the moment, and that is hopefully in a future talk we can have an expression over here that characterizes the behavior of some of these systems. Okay, if I'm permitted to carry on, I can talk about a few more benefits of actually having a normalizing flow approximation for this density. So the first thing,
Romit, can you wrap up in 5 minutes, please?
Okay, sure. I just wanted to very quickly mention that since you do have access to the ability to sample from this density that you've learned, because normalizing flows are also samplers, you can use the fact that the SD, if it's a Brownian type of SD, has a generator that can actually help you extract the drift and the diffusion from this particular system. So for example, here's a double well system, which we learned through a normalizing flow. And then when we estimate the density and drift from the normalizing flow, we are able to actually get sufficiently accurate results. Again, this is something that we are working on at the moment. So that was pretty much it. We have some work that's ongoing, and for example, relaxing Markovian assumptions, trying to improve the architecture of the normalizing flow, of course, and also apply it to like climatic type of data sets. So a lot of interesting things going on, and I'd be happy to talk to any of you if you have any criticism, any feedback, any suggestions that could make this work better. We are very, very interested in learning from all of you. So with that, I would like to thank you again for the excellent questions and for listening, and feel free to reach out to me at any moment now and beyond. Thank you.
Thank you very much, Romit. Sorry, some that on me. Right. We have 4 minutes for questions. Then 1:15 we'll start. You'll introduce Xiaoliang.
So questions for Romit?
Excuse me.
I have a quick question. For when you said that the determinant for the Jacobian is just e to the mu. Where did the derivative of nu go?
Let's see.
So you have this term in 25 that involves nu, right? So when you take the Jacobian, I expected to see somewhere the derivative of nu with respect to x.
So that's the Jacobian, but when you take the determinant, there are some off-diagonal terms which are zero. So they kind of get rid of the derivative of mu because of that.
Okay.
Yeah. So,
but does this make sense that somehow nu has no effect on the determinant of the Jacobian?
yeah. So the idea is that the e raised to the mu is kind of like your scaling term, and the nu is your translation term. So the scaling term controls the expansion of the space or the contraction of the space. That's kind of
okay. All right. Thank you.
Handy from WPI, do you have any questions? Handy is working on similar topics.
Oh, great.
Do we have more questions for Romit?
Sorry.
Can I ask something?
Yeah, please.
My name is Nicholas. I'm a PhD student at Johns Hopkins University. I have perhaps a naive question in terms of what exactly it means physically for a dynamical system that is from climate modeling to have an invariant manifold. I can understand this in terms of chemical reactions, but I don't have a good intuition for climate modeling, to be honest.
So you're not the only one to not have a good intuition about how climate models work, or how they correspond to some other systems that are well understood mathematically. But the one idea that I guess we should keep in the back of our mind is the climate or the weather, well, more the climate to speak, has this sort of what we call a climatology, right? So the climatology means that if I were to look at temperatures in the Northern Hemisphere at a certain location on the 1st of January throughout history, if I have access to the records, then they would generally not be, like say 50 degrees Celsius, if I'm looking at a, certain region sufficiently far north. So what does that mean? It means that there is this sort of, if you look at the average temperature at a certain location, you get this sort of, you'll get noise naturally because that's a function of the weather, but the trend will always be, in the Northern Hemisphere, cooler in the winter, warmer in the summer, and then so on, right? So, so in some sense, that is this sort of, you can say this invariant manifold. So the climate scientists like to call it, the attractor, so to speak, of the climate. So you have like a chaotic attractor which corresponds to how the Earth warms and cools itself because of the rotations of its axis. But on top of that, there are other processes that cause fluctuations from that, which correspond to weather or subseasonal effects. Now, the question is, okay, this invariant sort of behavior is actually controlled by many things, such as fossil fuel emissions. It's controlled by, anthropogenic activity. So can you quantify the effect of these processes on how this underlying manifold might change, right? So that's the question. So I hope I started answering your question. I mean, maybe I could not give you a precise type of definition because I don't.
Thank you. Yeah, that helps a lot. Thank you so much.
So thank you, Romit, for tuning in, and thank you for the presentation.
Am I expected to leave now? I don't know, or can I stay and listen?
It's up to you, Romit. Up to you to stay or not. It's an open, so there's no, anybody can sign in, and so
yeah, I'll stick around then. Yeah,
you can afford. Yeah, sure.
Yeah.
Thanks for joining us.
We'll move to our second speaker, Xiaoliang.
Xiaoliang.
So second talk is about deep adaptive sampling for solving high-dimensional PDEs. It would be presented to us by Professor Xiaoliang Wan. He is a professor at the Department of Mathematics and Center for Computation and Technology at Louisiana State University. He received his PhD from Brown University in 2007, and prior to joining LSU in 2009, he was a postdoctoral research associate at Princeton University. His research interests include stochastic modeling, numerical methods for stochastic PDEs, and scientific machine learning. With that, I would want you to start your presentation. Thank you.
Thank you for the introduction, and I'm very happy to be here to give a crunch talk, although remotely. Currently, machine learning techniques are actively being explored in scientific computing. And today I want to focus on the statistical error in machine learning techniques for the approximation of PDEs. I'm graduated from Brown. I was George's previous PhD student. So I have a background in scientific computing. So basically, I'm interested in the errors for the approximation. So quickly, this is the outline. I'm going to start from a simplistic case, which is functional function approximation. We compare the setup of classical approaches and the machine learning techniques to identify the sources of the errors for machine learning techniques for function approximation. Then we move on to the approximation of PDEs. Hopefully we can figure out some useful strategies to refine the training set, which contain the random samples. And of course, they are very important for the accuracy of the approximation. Finally, I'll show you some numerical examples. So for function approximation, usually when we talk about the classical approaches, we start from a given function. The function is given, right? With some kind of regularity. And then we choose some kind of function space, and we talk about the best approximation in this function space with respect to a certain norm. For machine learning techniques, for example, for the supervised learning, usually we don't know the function or the information, the target information in advance. We don't know the model. We want to learn the model. So basically, the starting point will be a little bit different. We only usually start from a set of data, right, instead of the given a given function. So basically, all the performance of the model should be understood from more appropriately from the statistical point of view. So instead of exact quantification of the error. So more specifically, for the continuous least square method, usually let's see with the Hilbert space with the weighted L2 norm. Here, we can assume that this weight rho x is the probability density function just for convenience. And then we can, write down a continuous least square method, which is optimization problem to optimize the L2 norm between the model and the target function, right? That is what we do in classical approaches. And if we don't talk about the data, we talk about the machine learning technique instead of the underlying distribution. Basically, we are looking for the relation between two random variables, right? X is the input, Y is the output. We want to look for the model between X and Y. Then we can also define this objective function actually with respect to underlying joint distribution, which also in the L2 sense. So basically, if we assume this joint distribution is given by this guy, so delta function in terms of gx, and the prior distribution for x, basically we have the same formulation for both classical approaches for function approximation and a supervised learning technique. But For the implementation, it's different, right? For the difference mainly comes from the implementation. For the machine learning technique, we need to use some random sample usually. So let's just look in terms of this simplified case. Let's look at the error. What does the error look like? If we choose, we don't, for now, we don't consider complicated model. We just use a linear space, the polynomial, right, as our to construct our model. So basically, we can consider two approximations. One is f star x is the best approximation given by given in the classical L2 sense, and this f hat star x is also the best model given by the machine learning technique. Of course, we usually optimize the different objective function. So since the approximation space is quite simple, then the optimal parameter actually can be given by two linear systems, right? One for the function approximation, the best approximation given by this linear system, a w star equal to b. For the supervised learning, another linear system, a hat times w hat star equal to b hat. The only difference is the approximation of the integral is different. Basically, for the supervised learning, we consider some kind of discrete L2 norm with respect to the random samples. So this a hat ij is kind of the Monte Carlo approximation of this L2 of this inner product with respect to this rho x. In classical approaches, usually, we can, to compute this this mass matrix, we usually choose some Gauss quadrature point in terms of the underlying polynomial, such that usually we can assume we can achieve a very high accuracy, even a machine accuracy. And for machine learning techniques, so we need to choose some random sample, meaning that we need to consider Monte Carlo approximation. Basically, the accuracy will be decided by what kind of sample you choose and the sample size n, right? So for the linear system, we can do stability analysis rigorously, since if we are able to quantify the perturbation given by delta A and the delta B, right? And that is not difficult to do if we consider a linear approximation space. And if you consider the approximation, the best the optimal model given by the machine learning technique, which is the f hat star. If you consider the error, you will see the error has two parts. One part is this one, G minus f star, that is actually the approximation error given by since f star is the best approximation given by the linear space, the chosen linear space. And the other part is the stochastic error induced by the random samples. So basically it's an error of Monte Carlo approximation. Simply speaking, when we apply machine learning technique to function approximation, or the approximation of PDE, since the only difference for the approximation of PDE is that the information, the targeted information is given implicitly, not explicitly. So basically, we have two types of error for the approximation. One is the approximation error given by the approximation space, and the other one is the stochastic error given by the Monte Carlo approximation of the objective function. So the existence of this stochastic error is both good news and bad news. It's bad news because it might be very difficult to reduce this error. We know the Monte Carlo approximation has a very slow conversion rate. The good news is in high dimensional space, maybe we don't need that many samples to get a reasonable reasonably small small stochastic error, because for high dimensional problem, usually it's very difficult to choose a linear space to get a very small approximation error. But anyway, we need to pay attention to both types of errors, because for machine learning technique, actually we are considering a trade-off between these two types of errors. And also we see that the stochastic error is actually closely related to the training set. Here, we use the random sample in the training set to approximate some inner product. And that's the reason we get a stochastic error in the final approximation. For a more general scenario, in statistics, you can talk about this excess risk, where you need to introduce some Rademacher complexity of the hypothesis space to bound the error. But here in this talk, we are not interested in the bound of that error. We're interested in how can we choose different random sample to reduce the stochastic error. That is the main target of this talk. So we, for the approximation of PDE, we make it more specific. We consider the formulation of PIN, and it's a very popular machine learning technique now for the approximation of PDE, and proposed by George's group. And basically, it's also the underlying framework is also the least square method, and so we replace this linear approximations, linear function space with deep net, right? With the deep net, and then we construct a loss given by the residue of both the equation and the boundary condition. So then an optimization problem can be written down, and to minimize this residue, the total residue, such that we are able to find parameter theta that give us a good approximation of the PDE solution. Of course, there are many other formulations for the approximation of PDE. And now we look at the discretization of PIN, and seems actually a similar story. The integration of the residue will be approximated by samples or the Monte Carlo method. And since usually we consider L2 norms, so the samples usually generated uniformly from the computation domain and the boundary. And in general, right? Of course, you can specify some prior knowledge to get a better random sample, better set of samples. So basically, we're going to discretize. Now we're going to optimize this, discretize the loss, right? Instead of optimize J, we optimize Jn. And due to the Monte Carlo approximation, we introduce some stochastic errors because we use some random samples from both the computation domain and the boundary. And generally speaking, we also have this stochastic error and approximation error, right? So for example, if I see this UN theta star is the minimizer of J, and this UN theta n star is the minimizer of Jn. And we are interested in the accuracy of UN theta n star, right? Theta n star. And we look at the error of this guy. It can be written split into two parts. One part is the approximation error, and that error is mainly determined by the modeling capability of neural network. And the other error, the stochastic error, will be mainly related to what kind of samples and how many samples you use to discretize the loss. So,
Xiaoliang, can I point out something that in
yes.
practice, actually, the biggest error will be the optimization error. which there are three types of errors: the approximation,
yeah,
the
right.
empirical error that you have here, and the optimization error. And in practice, we are basically bounded. I mean, that's why the accuracy is never better than
here.
5.
Here I don't.
So here you assume better. You assume perfect optimization error.
You're sure. I don't take into the account the algorithm, the optimization algorithm. So just just for you're right. Just for simplicity.
Yeah, I'm just saying that in practice, the optimization error is the big elephant, not the small elephant.
Yeah, for many cases it's true, but for if your problem is not good enough, I'm not sure. So because I mean, I'm trying to argue that if your PDE has some kind of singularity, and you made the stochastic error may be dominant.
Yeah, sure. Yeah.
Yeah, it's a complicated problem. We need to, balance too many errors. That's true for sure. So just want to, point out, for some kind of extreme case, but it's possible. Is let's see if we compare the, a bad scenario to the real event simulation. Let's see if your residue acts like an indicator function, and this B is a very small region in the computation domain. That basically means, let's just see, in a very small region, you have order 1 error, order 1 residue, but in other places, in the rest of the domain, the residue is just 0, right? The residue is just 0. Then if you want to increase the accuracy of your approximation, you must capture the small region that has order 1 residue, right? Otherwise, maybe in that area you have order 1, the approximation has order 1 error, right? So what I'm saying that if you just consider this Monte Carlo estimator, in the regular here, just the uniform, the sample will be a uniform. Then if you consider the relative error, meaning that the variance of this estimator over the integration, over this integration, right? This gamma can be small because the region for the region with the order 1 residue is small. This gamma can be very small, right? So, and if you want to get some improvement, you must have a small relative error. If the relative is large, basically means you cannot improve the accuracy in the region B very effectively. However, to capture that region B, just using straightforward Monte Carlo, you need this many samples to get order 1 error. Maybe it's so you need 1 over gamma, this many samples to only get order 1 error. Only get, you will get the approximation to gamma will be the error will be order 1. So if gamma is small, that means you need a lot of random samples to do that. And maybe we go back to the problem Monte Carlo simulation because we really cannot maybe we cannot afford that many samples. So of course this is kind of a bad scenario, but it's possible. So then we just start to consider this the reduction of variance, right? This classical technique, one classical technique for a variance reduction is the importance sampling. So basically, when we integrate this residue, we don't sample a uniform distribution, we sample another distribution. Of course, we all know the optimal choice is to sample with respect to the distribution induced by R squared, right? By R squared. But R squared is a very general residual so if you know, we in general, we are not able to sample R square exactly, right? But so we may need to consider, I mean, it's still possible to do importance sampling, use another distribution rho that is close to this rho star, the optimal distribution. So then we see, how about if I assume that we are able to find this another rho x, which is close to this optimal distribution in terms of this CKL divergence. And then if you look at the error of the integration given by the random sample with respect to rho x, it can be written as this. It has two terms. The first term is like a standard error of Monte Carlo simulation, right? The second term is it involved to some tail probability. So because when epsilon goes to 0, this R square over P should be go to a constant, which is C minus 1 here. So if P is very close to R square, this tail probability should be small. So then maybe we still have some chance to get some variance reduction in terms of this A. Maybe we can choose a small a if P is very, R square over P is very close to C minus 1. So that is, however, we are not able, actually, we are not able to quantify exactly how much reduction we can get in variance, because actually this Q divergence is kind of weaker than the L2 norm. You know, though for the approximation of PDF, we usually use Q divergence, right, and other similar.
What is P? Have you defined P?
P. Oh, I'm sorry. This should be rho.
Okay.
This should be rho. Sorry.
Yeah. Yeah. Okay.
Should be rho.
Yeah.
You know, you still have sharp eyes, huh?
Yeah. Sorry about that.
It happens a lot before. All right. So another way to consider the variance reduction is to generalize the definition of loss, where when we integrate the residue, we don't consider L2 norm. We integrate with respect to a different distribution, right? Like rho x. And of course, this rho x is absolute continuous to a uniform distribution. The minimizer, now here I only consider the residue induced by the equation. If rho x is simply, you know, strictly positive on the computation domain, you know, the minimizer is still like R squared should go to 0, right? The problem is well posed. And the possibility to consider different distribution is maybe with respect to this new distribution, the residue will be distributed like more or less evenly. So in other words, the variance of this R square may be small. So for the same number of, for fixed sample size, then this, the integral will be the Monte Carlo approximation will be much better since the variance of this guy is small. Actually, this idea is used, you know, by actually in this paper, right? Also from Crunch, where you know we just sorting some uniformly some uniform samples, then keep those with the largest residue. So basically, if the underlying distribution in the training set is not uniform anymore, so this integral is of course not with respect to the not a regular L2 norm anymore. It must be associated with the weight, right? But intuitively we know that we should put more samples in the region where the residual is large, right? If we want to refine the training set. But the simple strategy might have a problem, because it's like if you sample, if you have 100 samples, a natural question to ask is how many samples you need to keep, right? You need to keep one sample, you need to keep 10 samples or 20 samples. What is the best number of samples you should keep? So basically, we try to test a very general idea. So we want to approximate this optimal PDF induced by residue by a deep generative model, such that we are able to get some kind of variance reduction. At the same time, we can generate new samples very effectively. And for important sampling, actually, we have some choices, but also we have some requirement. We must need an explicit PDF model, because we need to compute the likelihood explicitly for the new PDF. And of course, we have some candidates for the classical models like mixture of Gaussians, and recently there are many other options given by deep generative models with explicit likelihood. And so, of course, deep generative model might be a better choice. And usually, when we talk about classical models, usually they are, quite simple. They don't have a strong capability for the PDF approximation. For the generalized case, where we don't need an explicit likelihood, we only need some new samples that is consistent with the distribution induced by the residue. So maybe we have more choices. Of course, we can consider PDF model or some sampling approaches given by MCMC or the variational stain method. Of course, some other deep generative models. And our choice is, we have proposed this so-called KRNet, is a flow-based deep generative model with explicit likelihood. Actually, it's one type of normalizing flow, which was just introduced in the last talk. So, the last talk, I don't need to, talk too much about the KRNet or normalizing flow. Actually, I only prepared one slide. So KRNet is simply one type of normalizing flow. It defines the invertible transport map with the structure of the North-Rossblatt rearrangement. So we integrate the structure of the North-Rossblatt rearrangement to the definition of KRNet to improve its modeling capability. So in the last talk, you see it's a technique called the real MVP. So if you're interested in, you can go, look up KRNet. In terms of the observable convergence rate, actually, KRNet has a double the convergence rate compared to real MVP for the approximation of PDF. Not, of course, not for the image processing. That's not what I'm interested in. So basically, the benefits, advantage of KRNet is something like this. First of all, it's explicit PDF model, and it has this explicit form, and it can be used as an effective approximator for general PDFs. Actually, we use this model to solve Fock-Planck equations. It performs pretty well, and also, this model defines an invertible transport map between the desired distribution and a prior distribution. The prior distribution, usually be chosen as a standard normal. You can also choose the more general prior, like the Gaussian mixture model, whatever. And this invertible mapping can, you map the prior distribution to the target distribution. So that basically means you can sample the prior distribution to efficiently obtain samples of the desired distribution. That is basically the benefits of the deep generative model given by the normalizing flow. So like I said in the lemma that although we are able to like approximate the target PDF, however, we are not able to quantify exactly how much reduction we can get in variance, but at least we can show it numerically, right? So see, this is a pretty irregular distribution. We are here, since the computation domain is usually compact, right? Here we actually approximate the conditional distribution given by this square. So the figure in the middle give you the sample from the model. You can see that for the Gaussian distribution in the corner, actually you only keep one quarter of the distribution, right? Because we only consider the conditional distribution in the square. And for this case, like you see for the variance, this is the variance in the standard deviation, not the variance, the standard deviation. So basically, the standard deviation can be reduced to 3%, meaning that for the simple sample size, for the same sample size, the approximation error can be reduced at least by 1 order of magnitude. And so basically, in classical approaches like finite element, we have 2 components, the mesh and the basis. And in deep methods, we have the samples and the neural networks. For the finite element method, the basis, we know it usually depends on the mesh, right? But for the neural network model, actually, it's kind of, it does not have a strong relation to the sample that we use in the training set. I think that should be something should be considered and addressed. And since we have 2 type of errors, the stochastic error and the approximation error, and those two type of errors should communicate with each other to get a better trade-off. So basically, a natural question is how if we are able to refine the neural network model further by manipulating the random samples in the training set. So then we just tested a very simple idea, which is similar to the adaptive finite element. So we consider 2 types of models, one model for PDE, the other model for the PDF, induced by the residual. So simply the scenario is like this. We use a neural network to approximate the PDE, starting from some random samples, either uniform samples or some samples generated according to some prior knowledge. Then we use a KRNet to approximate the distribution induced by the residue. And then we use the KRNet or deep generative model to regenerate the samples in the training set. We either replace all the samples in the training set for the important sampling. We all can refine the samples in the training set by increasing the number of samples in the training set. And then these 2 training process can be done alternately to refine the approximation of the PDE, and basically until no improvement can be obtained. And as I state, yes.
Can I ask a question? So on that point, how do you decide when to simply replace the distribution of the points, the collocation points, versus when to increase them? You said there are 2 choices here, right? In the sentence where you say refines training set, you have 2 choices, right?
Right.
So how do you decide between the two? That's what I'm saying.
Yeah, honestly, I don't have a definite answer for that.
No, in practice, I know. In practice, how do you?
But in practice, I guess the second approach should be more robust because you just add more and more points. It should be more robust. For the important sampling, you need to consider the inverse of a PDF, right? It might introduce some stability issue because 1 over small number is always a concern. But if you look at the performance in numerical experiments, and it's hard to say. Sometimes DSR may be better, sometimes DSG may be better. Maybe we didn't do everything properly. But
Xiaoliang, what is
yes.
what is the objective here? Is it to improve accuracy, accelerate convergence, or robustness? Because you said the word robustness. I thought
both can increase the accuracy. That's for sure. For some problem, of course, if your problem is good, is not necessary to consider something like this. I'll show you some example. If if the problem it's like bad enough, then of course you will get benefit from the adaptive sampling. That's for sure. So we just consider all the possible strategies we can try, and between these two strategies, actually, I don't have a definite answer which one is better. Or in some sense, I have not identified yet in what situation the one approach is better than the other one.
Okay.
All right.
Thank you.
No problem. So,
hello, Xiaoliang. This is Lulu. So I have one question here.
Sure.
Yeah, in this slide. So in this framework, when you solve the PDE, so first you iteratively train the PDE and also KRNet, then what's the cost of the training PINet? Or what's the internal cost compared to just standard SGD training?
The cost, if you talk about the order of the cost, I see the cost will be double. Roughly speaking. Actually, if you look at the performance of KRNet, the decay is very quickly. For example, for this case, I used like 10,000 samples, 10,000 samples to train KRNet. And so every time I generate 10,000 samples, and you can see that the decay is pretty fast, and for each iteration, this is not with respect to epoch, it's with respect to iteration. And for each iteration is basically for 1,000 iteration, you only need like a couple of minutes. So,
but you need to train this every time, right? You train a lot of times.
That's right. So that we have two, actually, that's a very good question because honestly, we don't know what's the optimal way to train these two models together. So initially we just tried the simplest way. We train one model, then we train another, then train the another one, back and forth. But actually you can train these two models simultaneously. And you basically, simply speaking, you let these two models talk to each other more frequently. And actually, it can have a better performance.
But it makes sense to freeze KRNet for a while, right?
Makes sense to what?
To freeze, to keep it, train it, freeze it for a few epochs, and then.
Oh yeah, sure, for sure. It's not necessary.
Just like quasi-Newton.
Yeah, that's right. You're right. So I mean, there are many possibilities actually to train two models, right? So I don't know. Actually, honestly, I don't know what's the optimal way to train to train two models simultaneously. It's also something we need to explore.
Okay, and then next question. So here, when you train the PRNet, you approximate the rho. Then when you do the refining, do directly sample from row, or you sample, let's say, from A row plus B, or basically a modified version?
No,
of
I
the
didn't
problem?
modify anything. I just use row to approximate the optimal distribution, and they sample directly from that row.
Okay, I see. So because currently I'm working on a very similar approach, but we do not have a KRNet.
Right.
Because we are working on 1D, 2D, 3D. In 1D, 2D, 3D problem, we can directly, or by brute force way to compute the row, right?
Right. That's right. Yeah, I mean, you're like what you have done in your paper. You have, another way to basically you are also approximating the distribution induced by R square, right? The only difference is you are not using deep generative model to do that. But we have the same idea, similar idea. We just tried different strategies. That's it, I guess.
Yeah, but my point is so we are kind of trying other ways. For instead of using the row to sample points, we use A row to the power B plus C. Then we can tune this A, B, C to sample points. And we found that
then that basically you also have a model, right? You also have a model. That's good, right? You also generated your own model to sample with respect to that model, right?
Yeah, and also we tried the actual example, this replace and gradually increasing, and we found that both works definitely. And it's with the one observation is if the number point is small, as in when we train this NK here is small, then the first approach, as you mentioned, is not robust, but second approach would be more robust.
Yeah, I mean that's what I'm saying. For important sampling, you do have that possible issue, right?
Yeah. Okay. Thank you.
No problem. So. Yeah, there's this analysis is pretty actually general. It's quite a standing point for the basically some standard results for the linear PDEs. And like I said before, it's very difficult to quantify exactly how much reduction we can get in the invariance. So basically, this is starting point for us to figure out some more specific conditions such that we can see something about the reduction in invariance to refine the analytical results. At this moment, I don't have much new to say about this analysis. All right, let's look at some numerical experiments. This is a 10-dimensional PDE, right? So I construct this example on purpose because the exact solution is something like this. Basically, it's a peak located in the origin, and so and on the boundary, and the solution is very close to zero. It's decay away from the center at the boundary. The U is almost to zero, right? So when in a high-dimensional place, when you consider a cube, most of the volume will be located around the corner, right? If you consider a sphere, most of the volume will be located on the surface. So basically, when the dimension increases because of the curse of dimensionality, the more difficult to find the useful information located in the center. So then, as you can see, for this case, you consider uniform sampling, and you see this curve that's given by the error of the approximate solution. When the dimension increases, and the error will increase accordingly to order 1. However, the loss behaved pretty well because most of the volume will be located around the boundary, right, where the residue is close to zero over there. So I think the optimization solver happy to focus on the boundary where you have most of the sample points and just ignore the information, the useful information actually from the center. So it's very difficult for the uniform sample to see the uniform information in the center in a very high dimensional space. So that's why Yeah.
Hello, sir. What's your number of training points here for this case?
I don't remember. Wait, let's see. I have someone. Yeah. Look at here. There's this one, the number of training points. So it increased from 50,000 all the way up to this what 200,000. For the uniform sampling, for this 10-dimensional case, for uniform sampling, the relative error remains order 1. If you consider adaptive sampling, you do see the improvement in terms of accuracy.
Because I see
I have a question.
Yes.
This is Michael from Utah. So I think you might have referenced a paper on this before, but it wasn't explicitly stated. So there's another method called residual adaptive refinement, and that's kind of naive, where you just throw points and you keep the ones that have high residual. So it's you're not building a model to sample that. I was just wondering, does that give you the same results as this method in the limit? I mean, if you take 10,000 epochs and every 100 of them you add points, does the distribution look similar to this method, or is this method outperform that?
Yeah, it's a good question. Unfortunately, we didn't. We don't have a direct comparison with the intuitive sampling because, like I just said, there are many choices for you to keep the samples. Like if you have 100 samples, how many samples should I keep? 1, 2, or 10? So I mean, if I keep too many samples, definitely, I don't see improvement. However, if I want to see improvement, maybe I need to try so many different strategies. I keep 1 sample, I keep 2 samples, and to me, it's it's like it's too much work, like to try all many possible case so many possible choices. But yeah, I mean, if you are, of course we can do that comparison. But I'm only not sure. Maybe I need to check, but I'm not sure. What's the criterion for me to keep the ratio? What's the proper ratio for me to keep the number of samples?
Well, I don't necessarily mean the ratio, because I mean, you could just use the same setting for DAS as you do for RAR, right?
That's right. That's right.
The same amount each one, and that would be a
I'll do that. Right, I'll do that. You should actually, actually, currently I don't have that comparison.
So I was just wondering if they.
Xiaoliang, I think Mike has a good point. I think I would have liked also to see that comparison just for standard vanilla RAR.
Right. Of course, I will do that.
Because everybody knows, Mike knows very well, and everybody that uniform sampling, even in 2D, in 2D, Mike has results that we've been discussing. Even in 2D, uniform sampling is very inefficient. Never mind the high dimensions.
Yep. I mean, like us, we need to. It's like said, we need to consider trade-off between the approximation error and the stochastic error. I think that the relation is quite complicated, and the different scenario, maybe we can, come to kind of different conclusion. But yes, you're right. Definitely, I'll do the comparison to because we, just future work, right?
All right. Yep. Thank you.
So, thanks. And so here is the behavior of the loss, right? Behavior of the loss. If you do adaptive sampling, and on the right-hand side, by the way, for this numerical result, for this numerical experiment, we actually trained the 2 models alternately. After we finish the training of 1 model, we train another one. So the communication between 2 models is not that often. So you can see actually the biggest improvement actually just come from the first adaptive sampling. first 1 or 2 adaptive sampling. After that, actually, I guess maybe, the most effective way to improve the accuracy is by increasing the sample size, I guess.
Hey, Xiaoliang, I have a few detailed question. So
yeah.
Here, so you first train the pin for 30,000 epochs, then you train the network.
That's right. They put it together. However, I think we use the same number of total epochs for the training of uniform samples and adaptive samples. So the training time also the training time instead of in terms of epoch actually are the same. You know what I'm saying?
Okay.
It's not like I only trained the model 3,000 epochs for uniform sample, then I stop. No. So like if I train 2 models, if like in total I trained like say 20,000 to 20,000 epochs, actually I keep training the model in terms of uniform samples for 2,000 epochs. The number of epochs actually are the same.
Okay.
Maybe actually some difference may come from the optimization solver, right? So that is still possible. There are some difference come from there. I'm pretty sure he didn't use LBFGS for the final refinement, I guess.
Okay, and then for the DASG, while gradually adding the new points, then how many do we add, or do we throw some existing points?
For DS, okay, I cannot remember exactly what's the number of samples. But for the DSR, meaning you add samples gradually. Actually, it starts with a few number of samples, not many samples. That keep adding some samples until you get the same number as the uniform sample. Something like that. It's like, for the adaptive finality, start from a coarse mesh, something like that.
Then each time, roughly speaking, how many samples do we add?
I guess it's like, it is something like this. If you want to, you have 3,000 samples. If you want to do like, see 6 times the adaptivity, you like, you just add 500 samples every time you do that, something like that. Very simple, nothing fancy.
Okay, I see. And for the left figure, it seems that for this case, the IA the refinement way is better than the gradually adding.
Yeah. That's right. Yes. I don't have a definite answer about which one is better. But for this one, it seems DR seems better. But eventually, they're the same, right?
Yeah. Eventually, will be the same. Yes. Yeah,
right.
Sure.
So this is the samples we generated from each adaptive stage, and of course, actually the samples will have a stronger and stronger tail, and meaning that the distribution introduced by the residual will be not like that localized, right? That's what we want to say. Yeah, my time is up. Maybe just say a few words about this high-dimensional commuter function. It's not with respect to pin. Actually, is its application to the variational form. For this commuter function, basically the very important quantity for you to quantify the transition in a stochastic dynamical system, and basically, if we consider this tau d, the first heating time for a region in the computation domain, and for 2 disjoint region A and B. You can consider A and B are two metastable states, two attractors, and we are interested in the probability that starting from a certain location, xt go to the state corresponds to B instead of A, and the heating time of to B is smaller than heating time of to A, and this is called the commuter function. This guy happened to satisfy this backward homograph equation, and it's a high-dimensional equation, high-dimensional PDE, right? So that's kind of interesting. There is a kind of interesting scenario here. So the solution can be formulated in a variational form, and you just minimize this H1 semi-norm in terms of this Gibbs measure. And this Gibbs measure, of course, can be a double well. And you can see it from here. This one well is located in A, one well is located in B, and this contour given by the solid line corresponds to the perturbed Muller potential. And this colors, this green colors, the changing green color give you the solution of Qx, and you can see from this direction to this direction, the probability given by Qx will increase, and it's 0 in the neighborhood of A, it's 1 in the neighborhood of B, and in the middle you see a jump, right? From 0 to 1, a quick transition from 0 to 1, it's like a step function. So if you solve this problem, see the scenario is quite interesting. So if you consider the integration, the approximation of this integral, one possible choice is you just sample this Gibbs measure, right? Sample this Gibbs measure and to construct a Monte Carlo approximation of this integral. Then you do the optimization, where you use a neural network to approximate this U. And However, when you sample this Gibbs measure, you will see, the density around A and B is higher than the density in between A and B, right? However, the main behavior of this commuter function occurs in the middle of A and B, right? So basically, when you sample the Gibbs measure, you get a few points in the region of interest, right? That's but however, people have implemented this approximate this commuter function, high-dimensional commuter function using neural network by using the sample from the Gibbs measure. It's very cost to generate this sample. Basically, you need to use MCMC to generate some samples from the dynamics given by SDE, and it takes like 24 hours to generate this many samples. That's because it's possible for X to go out of the computation domain. Then you need to wait until it comes back, and until you have enough samples between A and B, right? Between A and B. However, in that region, the density there is low, so it means you need to wait a long time. So we just tried a kind of a bold strategy. We just, we use KRNet to approximate the Gibbs measure given by the. Then we generate samples easily from that approximation, and then later on we just consider the whole thing as a distribution. And so we generate samples according to the whole integrand, right? So we take into account both the property of the potential and the property of the solution, and the whole thing can be done, in 3 hours. It's much cheaper, and for this case, like in the previous case, actually we don't let the two models talk too frequently. But for this case, we increase the frequency of the communication between two models. Actually, you can see that kind of like the distribution eventually stabilized. As you can see, this is this, there's the stage one, the sample for stage one. This is the sample for stage 33, this distribution of the integrand induced by integrand at stage 66, this 99. And you will kind of see a convergence of the distribution. And after we get this distribution, we are only able to increase the accuracy by increasing the sample size. We have no other choice. Now, anyway, quick summary. We just tested a very general and flexible adaptive learning strategy using the deep generative model for sample generation. Because the efficient sample generation cannot be done by classical approaches, right? Usually, the classical PDF models are not that strong enough. So basically, we see some improvement on the accuracy of the approximation PDEs when the problem has some low regularity, especially when the dimensionality is relatively large. Of course, we have many possible issues and problems to work on. And I think that's it. I'll stop here. Thank you.
Thank you, Xiaoliang. That's excellent. This is a very practical issue, actually, and could be tested in many problems. I have a visitor, Romulo. Rom, are you there? That he's actually struggling with this. Oh, yeah. Sort of empirically trying different things because he has a propagating front. It's a physical problem, so there's a propagating front. It uses all the flow around it, and it's really difficult to sample. He has tried empirically to sort of play that, but I was wondering if KRNet is it available on the GitHub?
It's available, but I tried GitHub, but eventually give up. I don't know how to use it. Of course, if I can share the KRNet, no problem. I think I put it on there, but I just later on I forget how to maintain it, something like that. So
you forgot how to maintain. You didn't water your plants.
It's available. It's available.
Okay.
Oh, sorry.
Ron, maybe you can reach out to Xiaoliang, right?
Yeah, sure, definitely. I need to try that because I've been trying some sampling techniques to see if I can improve the results. But until now, I could only get some success with like monocolor sampling. It's the best one, at least for now, for my problem. So yeah, I'll definitely try that.
Okay. Also, I want to introduce Michael from Utah. Michael from Utah is a student of Michael Kirby, Xiaoliang.
Oh, yeah. Okay, I saw Kirby's paper, right?
Yeah. So Mike is working on adaptive ideas, domain decomposition, and so on. So I think also your method will be handy. I don't think, you show us two examples, but I don't think really, the idea is great, the algorithm, but I don't think you test it in many diverse examples where we can actually and make fair comparisons. So that's one of my criticism, so to speak.
I don't have that many resources.
Yeah. No, I'm not saying that, but the jury is not out, so to speak, unless we actually do it in. Yes, the committer function is kind of interesting, and you see the benefits. But there's lots of physical problems where you have front propagation, you have localized events, coherent structures, and so on, and we basically cannot do that with random sampling like they are doing. So you do have to have a empirical raw to do it right, and then come up with strategies. So that's why I'm saying if you make your code available on GitHub, people will take it up and apply it to diverse problems. So
yes.
Yeah.
Definitely we can work together on so many problems, and that's
But maybe both Mike and Rom can reach out to you to get a copy of the code
Sure, no problem.
They work on diverse problems, so.
Right. Yeah,
Sure,
actually,
yeah,
yeah, that's right. I'm also interested into working on other problems, and it's a very interesting topic to me.
Lulu, do you have a paper on it, or you were still working on it
Yes, we are still working on it. Actually, I would say we try lots of things. Roughly maybe 6, more than 5 different methods, and maybe 5 equations, and we do the testing. So we are almost finished the work.
Okay, tell us when you're ready. You can come back here and
yes,
and show us your results. It is important because, of course, we want to scale up all these methods to bigger problems, and then that's where this becomes an issue, not just in dimensionality, but actually, let's say, fixed dimensions, but 3D domains and time.
Yeah,
it's so. But I like the fact that you have the time dependence there, and you're adjusting it, and so leave it to. That's what I'm saying. Make it public, and let crowdsourcing solve the problem.
Sure.
Any more questions for Xiaoliang?
Thank you, Professor Yan. So if there are no more questions, we'll close for today's seminar. Thank you so much for tuning in, and have a very happy and safe weekend.
Thank you.
Thank you very much.